Physics 251, Video Explainer 3, Problem 66. Astronauts use a centrifuge to simulate the acceleration of a rocket launch. The centrifuge takes 30 seconds to speed up from rest to its top speed of one rotation every 1.3 seconds. The astronaut is strapped into a seat 6.0 meters from the axis. What is the astronaut's tangential acceleration during the first 30 seconds? And part B, how many g's of acceleration does the astronaut experience when the device is rotating at top speed? Each 9.8 meters per second of acceleration is equal to 1 g. So, to solve for part A, the tangential acceleration, we will use this function where a tang is the tangential acceleration and it is equal to the change in velocity over the change in time. For this equation, we are given the change in time, and that is the 30 seconds to speed up from its rest to its top speed, and so we can plug that into our function, but we still need to solve for a change in velocity, and so to do this, we know that velocity is equal to 2 pi r, and then we divide it by the time. And when we do this, we get 2 pi times 6 meters, which is our radius, divided by the amount of time it takes for rotation, which is 1.3 seconds. And when we do this, we get a velocity of 28.999, or what we will be using for the rest of the problem, which is 29.0 meters per second. And as I stated, this will be our change in velocity. So when we plug that value into our tangential acceleration function, we get the tangential acceleration is equal to 29.0 meters per second divided by 30 seconds equals 0.97 meters per second squared. This is our tangential acceleration. For part B, we are solving for the number of g's of acceleration the astronaut will experience when the device is at top speed. So when the device is at top speed, there will be no tangential acceleration because the speed is not changing, but there will still be rotational acceleration. And so to solve for the rotational acceleration, we will be using this function where a rot equals v squared, or velocity squared, divided by the radius. And so we already know these. We already know both of these, and so we can plug them in. We plug in our velocity from part A, 29.0 meters per second, and we square it, and then we divide it by our radius, which is 6 meters. And when we do this, we get our rotational acceleration to be 140.17 meters per second. But because we want it in units of g, we just divide that by 9.8 meters per second squared, and we get 14.3 g's of acceleration that the astronaut is experiencing when the device is rotating at top speed.